Ordinarily, when we think of functions, we think of allowing all possible real numbers as inputs into the functions. For example, here's a function. The procedure is square, then add 3. I can think of taking -2 or -1 or 1.5 or even square root of 5, feed it through this process, and end up with one number or the other. This isn't the usual way that we write this sort of stuff, though. Instead, we use symbols like this. We write the name of the function, f in this case, and then beside its name, we write in parentheses the number that we are feeding through that process, and then we say that this is equal to whatever comes out of the process at the end. So we would pronounce this as f of -2 equals 7, f of -1 is 4, f of 1.5 is 5.25, and f of radical 5 is 8. Shortly, we'll have new types of functions, and we'll have a slightly different notation for them, but it's a very similar idea. Because these functions are of a different character than what we've seen before, we will give the stereotypical names for these functions. Instead of using f or g or h, typically we'll use things like a or b or c. There'll also be another notational shift. These new functions, the a's or b's or c's, are not going to accept just any numbers as their inputs, but only positive whole numbers, or positive whole numbers and 0, if that's convenient to us. So thinking of the square then add 3 procedure, I could think of taking 1 or 2 or 3 and so on, and feeding it through that process to get the output of the functions. If we were to use the usual notation, we could write this in the same way as for the f or g or h versions. But because we are not doing the same kind of inputs as we did before, people usually don't write it that way. Instead of writing a of 1, we'll write a with a subscript 1, which we'll either pronounce as a sub 1 or just a1. Likewise, a of 2 will be written as a sub 2, a sub 3, and so on. Generally, I can write a formula down that says a sub and then a number that represents a positive whole number or possibly 0, an equal sign, and then an expression that tells me how to calculate a number n. The difference between this and f of x equals x squared plus 3 is that on the f graph, you can have any x number, but on the a sub n graph, you can have only positive whole numbers or maybe 0. I can think of the graph of one of these things as well, but I just have to remember that for a function of this new type, which we're going to call a sequence, I don't have connected dots, I only have isolated ones. So if I started counting at 0, 0 squared plus 3 would be 3. There would be a dot on my graph. If n were 1, I'd have 1 squared plus 3, so I'd have a y-coordinate of 4, and so on. The difference between this and the graph of an ordinary function, f of x equals x squared plus 3, is I can put any x number in for x in this function, not just whole numbers, as is the case for the sequence for inputs. For a sequence function, the only kind of limit that is going to make sense to us is this sort. If I were to look at these numbers, a sub n, each of which is equal to 3 times n plus 1 over 5 times n plus 2, if I were to allow the index to become very large, is it true or is it false that the resulting a sub n numbers begin to resemble a certain particular number, or is it not true that that's so? If it is true, we're going to say that the an numbers converge to that value, and otherwise we'll say that the an sequence diverges. First, we'll look at some specific numbers to get a feel for what's going on. So, looking at the sequence given by a sub n equal 3n plus 1 over 5n plus 2, I'm just going to calculate some of these a numbers. I'll let n be 1 and 10 and 1,000 and 1,000,000, and as is obvious, as I continue calculating these things, the numbers are getting bigger, but they're not getting bigger in some sort of uncontrolled way. If I were to make a guess, I would guess that if I make this index on the a numbers big enough, that I can make the a number as close to 0.6, 3/5, as I like. Let's do some algebra and check and make sure that that's correct. So I can imagine asking this question: true or false, yes or no, by making the n big enough, can I make the distance on the number line between an and 3/5 less than 0.1, say? So I want to think of this as a yes-no question. If I make the n big enough, can I make the an as close to 3/5 as I like? Let me be a little bit more precise than that. If you tell me a distance, like 0.1 unit of distance, is there an index beyond which all of the an's are closer to 3/5 than this distance that you give me? For example, is there an index beyond which the distance from a number n to 3/5 is less than 1/10, say? It could be that this inequality is untrue no matter what n is. That's conceivable. It's possible that this inequality is true no matter what n is. That's possible also. It's possible that this is untrue for some n, but true for others. And what we're most interested in is this. It's possible that maybe this isn't always true, but after n is a certain size, then it is. At this time, we don't know which of those possibilities is true. We're going to do some algebra to see what happens. After making the bottoms of the fractions the same, doing some algebra to combine terms, it turns out that what I'm asking is it possible to make the absolute value of -1 over 5 multiplied by the quantity 5n plus 2 smaller than 0.1? When I take the absolute value on the left, the only effect that it has is to remove the minus sign, so we'll have to do some more algebra. Since both 5 times 5n plus 2 and 10 are positive, it's legitimate to multiply both sides of this inequality by 5 and 5n plus 2 and by 10 without altering the inequality symbol any. And I'll find out that the desired inequality is true when n is bigger than 0, which it always is if we start counting our sequence index at 1. So the answer to the question, can I make the distance from an to 3/5 less than 0.1 by making the index big enough, is certainly yes. Just make the index 1 or more, and that will do the job. So a person might well ask themselves then, all right, is it possible to find an index beyond which this an minus 3/5 distance is smaller than 0.01. Since we've already calculated a formula for this absolute an minus 3/5, there's no need to do that again. I need to decide if it's true or false that beyond some particular index n, that this quantity is smaller than 0.01. So I have to solve a similar inequality again. Since the algebra that we have to do is very similar to what we've done already, I've just written the steps down. This time the answer is still yes, but the n needs to be at least 18 over 5. N has to be a whole number, though, so the next biggest whole number after 18 over 5 would be 20 over 5, which is 4. If n is bigger than 4, then the difference between an and 3/5 in terms of how far apart they are is less than 0.01, 1 over 100. So we've seen that by making n big enough, we can make this distance smaller than 0.1 just by making the index positive. We also saw that we can make this difference in absolute value smaller than 1 over 100. Obviously, you could continue asking this question: could you make this distance smaller than 1 over 1,000? If you go through the algebra, the answer turns out to be yes. There is an index beyond which this difference is smaller than 1 over 1,000. You could then repeat the question for 1 over 10,000, 1 over 100,000. You could ask that same question for any small positive number that you care to. So sort of a meta question, a question about questions. If someone gave you a specific positive number, is there an index beyond which this quantity is smaller than that positive number? The answer to that question is either yes or no. If it's yes, then if the person kept asking about 1/10, 1 over 100, 1 over 1,000, and so on, and asked if the question is always going to be yes, the answer would be yes. So let's do the algebra. I'm going to select some number epsilon. It might be 0.1 or 0.01 or 0.001. All I know about the epsilon is it positive? I want to know if by making index n big enough, I can guarantee that absolute value of an minus 3/5 is smaller than this positive number that you were handed to start with. Doing the algebra, the requirement that absolute an minus 3/5 be less than epsilon reduces down into the statement that n needs to be at least 1 over 25 epsilon minus 2/5. We're thinking of the epsilon as being a small positive number, so 1 over 25 epsilon will be a large positive number, and then I subtract 2/5, so I still have a large positive number. Of course, this number, 1 over 25 epsilon minus 2/5, may not be a whole number itself, but that's not a problem. Figure out the value that we've just stated, and if need be, move to the right until you hit a whole number. If your index is bigger than this number, then the inequality we want will be true. If the index is bigger than capital N here, then it is automatically bigger than the cutoff for our condition. So if the index is beyond this number capital N, absolute an minus 3/5 will be less than epsilon in absolute value. The answer to the question about the questions is Yes, this motivates our official definition for the limit of a sequence. If I give you a sequence of numbers, a sub n, with indexes from 1 to infinity, if for every positive number epsilon there is an index n, so that if index I is bigger than index n, you're guaranteed to have absolute ai minus l smaller than epsilon, then we're going to say that the limit of the sequence is L. We'll say that the sequence converges to L. If anything else happens, then we say that the sequence diverges. In the next video, we'll see several examples of sequences. We'll introduce something that we'll call the f of x trick. We'll introduce two new concepts, a bounded sequence and a monotonic sequence, and then we'll convince ourselves that if you have a sequence that has both of those two previously stated properties, then that sequence automatically converges. Until then, I hope everyone's having a good day. I'll talk to you again soon.